Okay, so now what we're gonna do is we're gonna prove that if we've got uh these segments drawn from this point, one segment goes through the 2 points, and then the other segment is tangent, then you know that essentially the square on BD is equal to the rectangle on AD and CD. Now, to prove this, we're going to first draw in a few key lines. So first we'll draw EB. So drawing in EB, we should see that this is going to be a 90-degree angle because we have the theorem that says that if DB is tangent, then it must be perpendicular to the radius EB. So we know that fact, and then we're also going to draw DE. Right, so DE looks like this. And then we're going to do another thing. We're going to draw in, let's say, EF with a special characteristic for EF. So EF needs to be perpendicular to CA. And okay, so what's special about, let's say, EF? So EF has it so that way since EF is perpendicular to the chord CA, then we know that when we bisect a chord, or that when we have a line from the center that's perpendicular to the chord, it bisects the chord, and the other way is true as well. But though we have it that from the center to here, right, it's 90 degrees, so we know that CF is the same thing as FA. So CF equals FA. Now we leverage our previous proposition and we should look at DA. So DA, right, has CA bisected at F. So then this means that DA times DC plus CF squared has to equal DF squared, right, by the proposition that we proved previously, because F is the midpoint. Now let's draw in CE. Draw CE. And now that I have it that CE has been drawn in, right, what can I say now? So let's see what we have. We have that DF squared. Yeah, that's fine. Okay, DA DCCF squared. Okay, so now what we want to do from this one is we want to add in EF squared on both sides of this here. So let's add in EF squared on both sides. So I'm going to get DA times DC plus CF squared plus EF squared equals DF squared plus EF squared. And now we have a nice result, you see, because now this, right, CF is this length plus EF is this length must equal CE squared by Pythagorean theorem. So by Pythagoras, this is equal to CE squared or EC squared. And I got DA times DC plus EC squared is equal to, and now if we look again, EF squared, this length, and then DF squared must be DE squared. So by Pythagoras again, but for the different right triangle, by Pythagoras, I'm going to get that this is equal to DE squared. And now I can say DE squared is equal to EB squared plus DB squared. And I need to show, what do I need to show at the end? I need to show that this equals, right, okay, we're almost done. Okay, so now we got that EC squared, EC is the same thing as EB, right? So let's write that. EC equals EB by radii. So then this means that instead of writing EC here, I could write EB. So it's DA times DC plus EB squared is equal to DE squared. But again, by Pythagoras, this, but now kind of going using the hypotenuse. By Pythagoras, DE squared, so this length squared, right, is equal to EF squared plus DF squared. So is equal to EF squared plus DF squared. And that's equal to DA times DC plus EB squared. DE but that's not the one I wanted. Okay, this is good. DE squared is equal to this, but it's not the one I want. Let's look at DE again. Let's change our color and let's just slow down. Because look, this is, let's change it to something more contrasting. This is DE. And we have this line as EB and then this line as EF. And I saw this right triangle and said that it was this. But this is wrong. DE squared is also equal to, if we look at this right triangle, it's equal to EB squared plus DB squared. And I switched it because I realized that this is a result about BD, which is, BD squared, same thing. So now that's what I put in here and I get my result, because now I have DA, which is the same thing as, how do I write it? AD times CD plus EB squared is equal to EB squared plus BD squared. And then I could subtract out EB squared on both sides and I get the result that I needed. And it's just nice to go through this over and over, because this picture I should have drawn a little bit bigger. I apologize.